The operating system has two modes, kernel mode, which is referred to as 0, and user mode, referred to as 1. The kernel mode contains privileged instructions since it has the ability to alter operating system properties, like resources or input and output. The kernel system code directly accesses the hardware and memory in the system, while the user mode runs user applications. Today we will be taking a deeper look into a microkernel, which is broken down into separate processes known as servers. Some of these servers, like device drivers, run on user mode, while others, such as CPU scheduling, run on kernel mode. Each of these separate servers run in distinct address spaces. Since the servers are in such close proximity to each other, there exists a strong protection between them, irrespective of the kernel's mode. To make this simpler, let's picture a street. Each house on that street has a unique address, yet it's still on the same street. So memory management and CPU scheduling are like houses on that street. Both are on the same street, yet they reside in different address spaces. And just like smoke detectors are installed within these houses to protect people from harming themselves, the servers also have a similar safety system that provides internal protection. During the late 60s, there was significant growth in the size of kernels and the amount of source code being developed, which made the kernels difficult to maintain and contained many bugs. This was a rising problem and gave birth to the microkernel. The idea was very simple: to reduce the source code and allow easy management by separating services into user and kernel mode, while simultaneously increasing security and stability. Applications such as YouTube, for example, may request a microkernel for more memory management for uploading a video. This may in turn also request the file system to retrieve the video to upload to YouTube. The application has to make a call to the device manager, also called message passing, in order to contact the service, which in this case is a speaker service. From this, two steps have already been executed. The application is requesting speaker I/O access, and the microkernel is directing the execution to the device manager. Another two steps are executed when the speaker returns back to the microkernel with access, and the microkernel goes back to the program YouTube that has requested its services. Four steps are executed through message passing, which created overhead due to the amount of message passing calls. One of the first actual microkernels was developed in the 1980s at Carnegie Mellon University, called MAC, which led to the Darwin being created, which was a loosely based microkernel approach, also known as Mac OS X. The microkernel also influenced Windows NT, which was based on a layered microkernel. Unfortunately, it performed worse than Windows 95. This Mac gave birth to Darwin, which is now known as Mac OS X, being loosely based on the microkernel approach. However, performance of the microkernel was very weak due to Windows NT, which had a layered microkernel and performed worse when compared to Windows 95. Now that we know about how the microkernel originated, let's find out how it works. Now, let's discuss the positives of microkernels. It's relatively easy to extend a microkernel. It's easier to migrate the operating system to a newer architecture. In theory, a microkernel is more robust than a monolithic structure, quickens the development process, and is simple and easy to maintain. Now let's discuss the disadvantages. Microkernels require heavy resources, debugging can be extremely cumbersome, process management can be very complicated, there's a risk of